Hi folks, this series of videos are going to deal with optimization problems. So problems where we're looking for a best case scenario for a given problem. All right, so here, let's take a look at this one. We've got a table salt producer needs to design a 100 centimeter cube container, but wants to minimize the cost of materials. And in A, it says, what dimensions would minimize the amount of cardboard used to produce a cylindrical container? Okay, so it makes sense if you're using cardboard to produce the container, we want to use as little of it as possible. Okay, so when we're talking about a cylindrical container, we should be thinking about the surface area, so the exterior of the container. Now, while it will have a thickness, presumably we'll assume that the thickness is constant throughout. So we're just going to be dealing with the surface area. All right, and then the second one, they actually give us a little more to work with. It says, would the answer be the same if it's determined that the diameter needs to be between 3.5 and 4.5 centimeters? So what we're doing here is we're giving a constraint. Okay, so this problem here has a natural constraint in that our dimensions need to be greater than 0. But now we're going to add in the second problem another specific constraint that the diameter has to be between these two numbers. So that might have to do with market research that determined that this is the best interval of diameters for this particular product. All right, so let's take a look at A. So if I want to minimize the surface area of this cylinder, let's start by drawing a cylinder and recalling how one finds the surface area. Okay, so the two dimensions here that we're interested in are the radius and the height. And we know that the area is equal to, well, 2 times the top and bottom, so 2 times the area of this circle, so 2 pi r squared, plus the area of that side portion, which is just given by 2 pi rh. So remember that 2 pi r represents the circumference, and it's like you're folding out that side part, and then you're multiplying by the height of a rectangle. So there's your 2 pi rh. All right. And this is going to be the function that we want to optimize. So in other words, we want to find the minimum value, in this case here, where our dimensions are strictly greater than 0. That's going to give us the smallest surface area. This is where we run into our first problem. So step 1 was to determine what we needed to optimize. Step 2 in this case here is going to be to take this equation given with 2 variables and write it as a function of 1 variable, since the calculus we know how to do only deals with functions of 1 variable at this point. All right, this is where they gave us yet another constraint. Beyond in B, where they give us a constraint on the diameter, we notice that they told us that the volume has to be exactly 100 centimeters cubed. Okay, so you will look for this constraint to find a way to write one of these variables in terms of the other. Okay, later on we'll see other options available to us, but this is what we're going to try to do now. All right, so I know that the volume of a cylinder is given by pi r squared h. Okay, the area of the circle times the height. So they also tell me that the volume is equal to 100. So I have 100 equals pi r squared h. Okay, and so here I realize that I can solve for r in terms of h or h in terms of r. Now in this case here, if I only had an r squared in my area formula, I might be tempted to solve for r squared. But because I have an r on its own, I realize that's going to involve taking a square root. Whereas if I solve for h, so in other words, divide by pi r squared to the other side, I'm going to have something that works much nicer, something that doesn't involve having to work with square roots. Okay, and now what I do is I'm just going to perform a substitution like you've done in the past. So now wherever I see an h, I'm just going to replace that by 100 over pi r squared. And let's see what that gives us. So area now is pi r squared, 2 pi r squared plus 2 pi r times h, which now I'm writing as 100 over pi r squared. Okay, and in fact, let's simplify here because pi's reduce and this r in the numerator reduces with one of the r's in the denominator. So what I've managed to do now is to write a as a function of only r. Okay, so 2 pi r squared plus 2 times 100, so 200 over r. Now, I could have certainly isolated r and done the same thing and written the area in terms of the height. This here just seems easier. Now, if you think back to when you solved optimization problems when you were doing quadratics, you were able to do that because your model was always a quadratic function, and so you could just complete the square to determine the max or min. Whereas here we see we do not have a quadratic. So this is where we now can use calculus to determine the minimum of this function. So this is where now we're going to use our calculus methods to finish off the problem. So step 1 is to determine where the derivative is equal to 0. Okay. Now, one thing that I do want to add to this model that I've come up with is I want to make sure that I'm specifying the domain over which I'm working. So I'm not interested in negative r values. So you want to specify this just to make sure that you're working within that context. All right. In part B, my domain would be 3.5 to 4.5. All right, so let's take the derivative here. So this one's nice and easy. 2 pi is just a constant, and the derivative of r squared is just 2r. So I'm just going to have 4 pi r. And here, I'm going to think of this as 200 times r to the minus 1. Okay, so 200 is just a constant, and the derivative of r to the minus 1 is negative 1 times r to the negative 2. All right, and I want to determine when this is equal to 0. Okay, so we have 4 pi r minus 200 over r squared. And this is something relatively easy to solve. So I'll bring this to the other side. 200 over r squared equals 4 pi r. Okay, multiply both sides by r squared. So I get 200 equals 4 pi r cubed. And so now I can solve for r. So first I'll divide by 4 pi. So 200 over 4 pi. And then I'm going to take the cube root to solve for r. All right. Now, since we're working with a physical problem, I'm going to work with an approximation here and not keep it as an exact value. Okay. If it was a purely mathematical question, I'd keep the exact value. All right. So here, let's do that. We'll do 200 divided by 4 times pi. Make sure you put your brackets there to make sure it calculates correctly. Okay, and then I'm going to take the cube root, so the exponent of 1 over 3. Okay, and we have 2.515. Now, because we're not working on a closed interval, I can't just check the endpoints and the critical points. So here I've got only one critical point. You know, by the way, in our domain, the derivative always exists because here r equals 0 is not included in our discussion here. But what I don't know is, does this in fact relate to a minimum? And does it relate to an absolute minimum? So this is where I need to show that. So we do that by testing the sign. So I'll use that first derivative test. So if I take the derivative of a and I create a number line, remember, I'm only interested in numbers bigger than 0. Okay, and here I've got 2.515. So on the left, let's pick something like 1. All right, so I'll use this reduced version, or sorry, simplified version of the derivative to help me find this. And I think I might even be able to do this without a calculator. Certainly I could stick it into my calculator. So here 4 pi times 1, so this is just 4 pi, which is about 12, minus 200 divided by 1 squared is 200, so this is clearly negative. So that's a good start. And now let's pick something like, I don't know, 5 here. So 4 times 5 would be 20 times about 3, so that's about 60, a little over 60, and I'm subtracting by, well, 200 over 25 is only 8, so this is definitely going to be positive. Of course, you can just stick this into your calculator just to be sure. Okay, but let's see what this tells us. This tells us that this function, okay, has a minimum at 2.5, and we know that to the left is always decreasing, okay, and then to the right is always increasing, and there are no other critical points. Okay, the function is always going to be increasing, so how it increases doesn't matter. All I know that it's continually getting bigger. So that tells me that 2.515 is indeed, on r greater than 0, is an absolute minimum. Okay, so we've solved the first part of our problem. And so now what I need to do is go back to the question and see what they're actually asking me to determine. And what they're asking me to determine is the dimensions that minimize the cylindrical container. So it looks like I've got one dimension. I've got the radius. So now let me use this formula here to find the height. So the height is going to be 100 over pi times 2.515 squared. All right, so let's put this, estimate this here. So 100 divided by, okay, pi times 2.515 squared, and that's 5.032. Okay. And so now I'm going to write out a sentence in a second, but I'm wondering if you notice something here between the radius and the height. Notice here that the radius is exactly half of the height. Okay, so that means that the diameter, just twice the radius, and the height are going to be equal. Now you might remember that back from grade 9, where we determined that the optimal cylinder, okay, with no other constraint than knowing the volume, was going to be the cylinder for which the diameter and height are the same. So in other words, the cylindrical equivalent of a cube. Okay, we're going to see that this isn't always the case when we start adding other constraints like we have in part B. Okay, but this is a nice result because it's perhaps something familiar. Okay, so here our dimensions are 2.515 centimeters for the radius and 5.32 centimeters for the height. All right, there we go. So before we move on to part B, I just want to use this as a way to come up with an algorithm for solving these problems. All right, now there may be cases when the model is given to you directly, but here step number 1 was to determine a model for the variable we're trying to optimize, in this case here, area. Step number 2, again, it won't always be necessary, but in this case it was, is write that model in terms of one variable using whatever constraint is given. So that's what we did by rewriting h in terms of r and then replacing it into the equation. Once you have your model in terms of one variable on your specified domain, you then use your calculus methods to determine the max or min. Okay. Now, because we were not working on a closed interval, I needed to justify my answer. And then, of course, remember to always look back to the original question to make sure that you're answering what they are asking for. Okay, so your notes will look like this, and we see exactly those steps. So write the equation to be optimized, use any conditions to write the equation in terms of one variable, determine the constraints on the variable, in other words, the domain. Okay, use your calculus tools to solve for the optimal value or values, and then make sure you answer the original question. All right, so let's just quickly finish off part B here, where now the domain, okay, of, in this case here, the of this function, the area function, is going to be, and it's in terms of diameter is what the constraint is given as, but of course we're working with radius. Okay, so we need the radius to be, well, half of 3.5 is 2.75. Okay, sorry, 1.75. Sorry about that. See, sometimes using a calculator is a good idea. And half of 4.5 is 2.25. Okay, so essentially we would be doing exactly the same thing as we did before. Okay, determine your, so now I'm working on a closed interval. So remember, it was determine your critical points and then test the y values at the critical points and at the endpoints. But we notice here that our critical point, 2.515, is not even in our interval. So we don't have to test 2.515 because it is not within the given domain. So since there's no critical points in this domain, I just have to test the endpoints. All right. So clearly our answer will be different than the answer in A, because it turns out that our critical point is not in the interval. Now notice here I could make an argument without actually having to calculate anything in this particular scenario, because look at our number line here. We see that to the left of 2.515, the function is always decreasing. Okay, meaning that if I've got 1.75 and 2.25, and I look at the y values, well, the y value at 2.25 must be smaller than the y value at 1.75. All right. Now, if you don't notice this argument, and this is because we happen to have already done this work, if you don't notice this argument, well, the other option is to just take these two values and throw them into the area formula and check. Okay, so let's just do it for the fun of it, just to make sure that this all makes sense. So I'm going to take the area at 1.75. Okay, so let's do that here. So I'm going to take the simplified version here with only area. So I have 2 times pi times 1.75 squared. Okay, plus 2 times pi times 1.7. Oh, sorry, I'm using the wrong one. So I'm going to delete all that. I'm just going to start over. I just realized I was looking at this one. I want to look at this one here. So 2 times pi times 1.75 squared. Okay. And then plus 200 divided by 1.75. All right. And what do we have? 133.5. Okay. So now let's take the area at 2.25, and this should be smaller. Okay, so we're going to do 2 times pi times 2.25 squared, okay, plus 200 divided by 2.25, and that's equal to 120.7. Okay, so in this particular interval, it means that this is my absolute max and this is my absolute min. So of course what I'm looking for is the min, and so our dimensions in this case here are going to be a radius of 2.25 and a height of, well, again, let's stick this into our equation, 100 over pi times 2.25 squared. Okay, so here 100 divided by pi times 2.25 squared, and that's equal to 6.3, or about 6.3 centimeters. Okay, and we see here that this does not have that characteristic that the diameter and the height are going to be the same. All right, so just quick recap. Remember our algorithm now. Determine a model, write the model in terms of one variable, give the domain of the variable, use calculus methods to find the optimal value, and then go back and make sure you're answering your given question. All right, that is this for the first one. We're going to go to a second one in the next video.